This video is about getting more power out of a Class D amplifier, and it corresponds to section 35.5 of Applied Analog Electronics. Let's take a look at what controls the power of the loudspeaker. Basically, we can think of the loudspeaker in the audio range as mostly a resistive load. The inductive nature doesn't really come in until we get to higher frequencies. So the power is just V squared over R. R is the resistance and V is the RMS voltage of the signal we're putting into the loudspeaker. Obviously, one way to increase the power would be to reduce the resistance of the loudspeaker. To use a smaller resistance loudspeaker, we can get more power for a given voltage. There's some limitations, though, to this, because if we wanted to get a very low resistance in the voice coil of a loudspeaker, we would have to use fairly fat wire. That fairly fat wire is going to have a lot of mass, and that mass is going to then cause a resonant frequency that's fairly low. It's going to make it difficult for the power to actually accelerate the mass of the voice coil, and we're going to end up with an inefficient loudspeaker. So in practice, the loudspeaker resistances that are available are small but not tiny. 8 ohms is the most common, perhaps, resistance for a loudspeaker. You will see 16 ohms, you'll see 4 ohms. It's possible to put a couple loudspeakers in parallel to get 2 ohms, but getting much smaller than that is not really very practical. So what we usually do when we want to get more loudness out of a loudspeaker is to increase the voltage. Now let's take a look at what mechanisms we have for doing that in the Class D power amp. We start out using our H bridge. And we've got 2 voltages. Let's call this one VH, or high voltage. And coming out of this, going to the loudspeaker, we are going to have a voltage across here that is at 100% duty cycle is going to be VH, because we're going to have VH on top. Let me actually just write this thing here. So VH, that's positive VH, because we'll have VH on top and ground on the bottom. But what happens if we switch to D equals 0%? We'll have minus VH, because we'll have ground on this wire and VH on this wire. So the maximum voltage range we're going to have going to the loudspeaker is plus or minus VH, so it's an amplitude of VH. And that's going to give us an RMS voltage depending on what the signal is. For a square wave, so if we have a low frequency square wave here, we'd have plus VH, minus VH, plus VH, minus VH, and the RMS value is just VH. But if we have a sine wave, we don't get the same sort of always being high or always being low. The average of the squared voltage is smaller, and we end up with VH over square root 2 as the RMS voltage. And if we've got some music signal, we're going to have VH times something called the crest factor. The crest factor is basically, or actually it's VH divided by the crest factor. The crest factor is usually given by the peak divided by the RMS. So the crest factor for square wave is 1, for a sine wave is square root 2, and for a percussive sound it can be very large, 10 even. And so what we end up with is the power that we get to the loudspeaker, the power that determines the loudness of the sound, depends not just on the voltage that we're putting into the H bridge. That determines the loudest sound we can get, the maximum power we can get, because the square wave here, that's the most we can get ever, is this VH. But with other sounds, we may get substantially less than that. And that's why when one gets a amplifier, generally the amplifier rating is much louder, now in terms of the power output, than what you would really expect to need in terms of, well, if I was putting out a sine wave, how much sound would I need to be, uncomfortably loud? Because a lot of the sound you're going to be doing, voice and music, has a fairly high crest factor. So you want to be able to get occasional large excursions, even though the average values, the root mean square values, are substantially smaller. Okay, so that's why we want to make it substantially louder perhaps than you might have thought if you just were doing calculations with sine waves. But how do we get it louder? We already decided that reducing the resistance of the loudspeaker doesn't help much, which leaves just increasing the voltage on the high voltage. And that sounds pretty easy. We can get transistors here that can go up to quite high voltages. And so we can make an H bridge that can handle a large voltage. No problem. What about driving the H bridge though? If we look inside that H bridge, let's just look at half of it, a half H bridge, because two sides are the same and save drawing time if I only draw one side. So we've got two transistors, the P FET and the N FET. And this is the shared drain, and this is our high voltage here. What does it take to drive this thing? Well, to turn this transistor off, we've got to take this got to go down to 0 volts, and it's got to go up to the threshold plus something. This may have to go up to, say, maybe it has to go up to 5 volts to turn on the transistor enough. It depends on what the transistor actually is. The threshold voltages for these transistors is one of the specs you get on the data sheet, and they can vary quite a bit. The ones that we were using in our labs were low threshold ones, so that we could operate this thing at 3.3 volts. But you can get power transistors that have like 5 or 6 volts before they start even to turn on. So let's look at sort of typical logic levels, 0 and 5 volts. What does it take to turn this one on and off? Well, to turn it off, we've got to take it up to VH, or very nearly. And to turn it on, we have to take it down to VH, say, maybe minus 5 volts. And again, the thresholds here depend on exactly what the transistor is, and you can get different transistors with different thresholds. So the 5 volts here is just an example. It's not, gee, all transistors are like this. Okay, now if our high voltage is 5 volts, everything's great. We've got 0 volts, 5 volts, and 0 volts, 5 volts. We have the same signaling needed for each transistor. We can just drive them from ordinary inverters or from comparators, depending on exactly what signaling we need, how fast we need to drive the transistors, and that's all what we've been looking at so far. But what if we want to take this high voltage up to 9 volts? That'll give us substantially more power, because remember, it goes with the square of the voltage. So instead of 25, we would have 81 for the square of the voltage. And so we're looking at something that's more than 3 times as much, even though the voltage has only gone up from 5 to 9. The power has gone up from 25 over the resistance to 81 over the resistance. If we're looking at an 8 ohm loudspeaker, that'll take us up to about 10 watts, which is substantially more than the 25 over 8 would be about 3 watts. So from going 3 watts to 10 watts is a pretty substantial change. But we've got a problem, because the signaling levels we want here are 4 volts and 9 volts now, and down here we want 0 volts and 5 volts. And those are not the same anymore. And furthermore, if we try to do something like the trick we used with using an inverter to make a digital amplifier for driving this gate fast, well, this one's no problem. We can drive this one because 0 and 5 volts are exactly the sorts of voltage we use for those inverters. But 4 volts and 9 volts are not. And we don't have a 4-volt supply sitting around. We've just got the 0 and 9 here. And I'm assuming, notice that we have got actually 2 power supplies here, that we've got the high power supply, the high voltage power supply for driving the loudspeaker, and a separate one, perhaps derived from that, that drives the internal logic that's running at the 5-volt voltage. Okay, so what are we going to do? Well, simplest thing is to come up with an amplifier of some sort that drives this transistor shifting the voltage. And let's take a look at one way to do that. Okay, what I've got here, Q1 on the bottom is the NFET that we had before. Q2 on the top is the PFET that we had before. I've got a 9-volt power supply. So all this is looking exactly as before. When I'm driving Q1, I'm doing that through an inverter. Here I've shown a Schmidt-Trigger inverter just to make sure that it produces a clean transition, even if the input's a little bit messy. So that's looking perfectly like what we've done before, using an inverter here, a Schmidt-Trigger inverter, to drive the NFET. Our input PWM signal is 0 volts to 5 volts. The inverter is driven 0 volt to 5 volt power supply. No problems there. What are we doing, though, to drive Q2? Here I've got what amounts to another inverter, but it's done in a kind of tricky way. I've got another NFET, Q3. This is a small NFET now, not a big one like the others, because it doesn't have to drive the loudspeaker output. It only has to drive a small chain of resistors here. And what happens? Let's take a look at what happens if the PWM signal is high. What does that do? PWM signal high turns Q3 on. That means that we'll have current flowing through the 9-volt supply, through R2, through R1, down through Q2 to ground. So when the PWM input is high, R1 and R2 are acting as a voltage divider. And the gate voltage on Q2 is the output voltage of that voltage divider. The resistance of Q3 is going to be very much smaller than R1, so we can ignore it. So R1 and R2 make a voltage divider. That determines what the voltage will be on the gate of Q2. And notice that it'll be a low voltage, R1 over R1 plus R2 times the 9 volts. If that low voltage is low enough to turn on Q2, we've got the output being pulled high, which is what we want when the PW input here is high. Because take a look at what's happening on the other path here. If the PW input is high, then pin 3 of the inverter is high, pin 4, the output of the inverter, is low, Q1 is turned off. So we've got PW input high, Q2 is turned on, Q1 is turned off, output is high, everything looks cool. What happens if we turn the PWM input low? Okay, let's look at the NFET first. If pin 3 of the inverter is low, then pin 4 of the inverter is high, and we're turning on the NFET. That's the NFET Q1. But PWM input being low also means that Q3 will be turned off. If Q3 is turned off, there's no current through R1 and R2 anymore, and R2 will be pulling up the gate of Q2 all the way to 9 volts, turning the PFET off. Okay, so we've got the NFET when the PW input is low, the PW output is low, Q1 is on, Q2 is off. Everything looks good. The tricky part of this design is getting sizes correct for R1 and R2. Notice that if R2 is large, then we'll have a large series resistance to the gate, Q2. And that means it'll be slow. Slow to turn off on the PFET is not a good thing. So we need to make R2 fairly small. But if R2 is small, and R1 over R1 plus R2 is what's determining the voltage for turning Q2 on, we have to make R1 small also. Well, if both R1 and R2 are small, then when we turn on Q3, we're going to get a large current through there. And all that current, it's not doing anything about driving the load, it's just heating up those resistors and charging up the Q2 gate. So it's wasted power in some sense. And so we have trade-offs here about how much power can we waste, how fast do we have to turn Q2 on, how fast do we have to turn Q2 off, and balancing all those different criteria make selecting the resistance values for R1 and R2 just a little bit tricky. Make them too small, you waste current. Make them too large, and you switch the PFET too slowly. If you have the PFET still on when you turn the NFET on, then you waste current for shoot-through current during that time when the PFET and NFET are both on. So it's a little bit trickier than the designs we had when we were driving the transistors directly from inverters or other CMOS amplifiers. Here we've got what's really an NMOS inverter. An NMOS inverter has just an NFET and a resistive load as opposed to putting a PFET on the top. So Q3 and R1 plus R2 form an NFET inverter. And the reason we could theoretically eliminate R1, switching Q2 all the way from 9 volts to 0 volts. The trouble is that's slow, because if Q2 is swinging a long way, then it takes a long time to charge or discharge it. And that might mean it turns on fairly quickly, it charges up, but gets to the point where it turns on, no problem. But so that's when Q3 is turned on, pulling down to ground. That happens very fast because Q3 would be small. But turning off gets slow, and the larger R2 is, the slower it is, and also the more the voltage has to swing, the longer it takes to remove that charge from the gate and turn the transistor off. So R1 and R2 give you a way to adjust how fast you turn Q2 off and how fast, and to some extent how fast you turn it on. But mainly you're limited by how fast do you need to turn the thing off and how much current can you afford to dump through R1 and R2 when the PWM input is high. There are other solutions to this problem, and basically almost every Class D amplifier designer comes up with different variants on the solution. The part that matters is that Q1 and Q2 are being driven by similar signals, but there's a voltage offset between them. Q1 is going between 0 volts and 5 volts for its gate. Q2 here is going from some voltage, perhaps 4 volts and 9 volts on its gate. And getting that separate control of the two transistors is important for going to larger voltages. And as you go to larger and larger voltages, 24 volts, 48 volts, sorts of voltages you would need for motors like wheelchair motors and stuff like that, the more important it is to get good control of the gates of Q1 and Q2. But this simple circuit would allow you to use a much larger power supply voltage than what we would be doing if we just did the simple designs we looked at previously, where we just used inverters to drive each of the gates. Because here we can run to voltages that are not limited by how much the inverters can withstand. And that's probably enough for now on how to handle high voltages in H-bridges.